Well, since it's almost time, might as well start. You know what? I'll wait 1 minute. I got like 30 seconds. Good. All right, you guys are here. I'm excited. This is the last one, yeah, of the year. is that here too? Oh, she is. Okay, cool. Question mark. Well, yeah, this is the last one, and I'm going to try to go fast because there's a lot to cover. But I'm going to try to make this as useful as possible, so I won't go too fast. I'm trying to keep it to the point and to what's on the final. What do you need to know? And I'll answer any questions and whatever else you might have. Okay, so there's the 18-second delay or whatever. So your question might pop up, and it just might take me a second to get to it. But just have patience. We've done this once or twice before, so I'm going to start for real. And let me just restart the recording because it'd be annoying if I didn't. All right, start recording now. All right, so we are officially started. And I know period 2 has the final tomorrow, so there's not really any more time for questions in class, but all the other classes you certainly can. Hello, Serenity. Hello, Amia and Aiden. And anybody else who's here who I can't tell. Nice. Well, let's not waste anybody's time. So, to start with, Unit 1 was all about kinematics of motion, and I did talk about that today in class. So really quick, while I'm chatting here, when you have a graph, surprise, we have graphs, you've got the y and the x-axis. So on the y-axis, on the x-axis, which variable goes on the y-axis? Do you remember, or does it not matter? So, if you had to guess, for example, on a multiple choice test that you might see in the future, well, they might ask you a question similar to this. On the y-axis. All right, not seeing too many replies, so I'm just going to tell you because, maybe you weren't sure. But that's going to be the dependent. It's always dependent versus independent. Yes. Hello, Noel. Nice to see you. All right. So there you go. That's it. I mean, just brief refresher. It goes dependent, independent. The shorter word goes here on the y-axis, and the longer one goes on the x-axis. So dependent, independent, whatever versus time is usually a distance versus time, displacement versus time. Anyway, it doesn't matter. So that's the answer to that. Alex, I think you're wrong. Wait, why is everybody saying A? How much of a delay do we have? Holy cow. I might be underestimating the amount of delay. Why is everybody saying independent? I feel like I'm wrong now. I should know this as a teacher, but now you've got me all thinking. Lexi says A. Everybody says A, except for Mr. Jern. Well, I'm completely bombing this first part if everybody's right. Oh boy, Ureli says B. All right, now I'm so unsure. I'm actually going to Google it right live streaming. So, oomph. Which variable goes on the y-axis? So, there you go. Dependent goes on the y-axis. All right, verified by Google. So, all right. Yeah, that's weird. I might... So we'll see what happens with that delay. I don't know if it'll get caught up or not, but all right, the answer is B for sure. I looked it up, double checked. Long delay. Dang, that stinks. All right. Well, maybe if I don't know, restart the stream. Well, I blame Google. Yeah, all right. Well, we'll do what we can. I apologize. I'll still see your questions. I might not see your answers beforehand, though. All right, yeah. Holy cow. We're still talking about the delay. All right, well, good to know. So now we know. I haven't timed it yet, but it was 18 seconds before. All right, well, moving along then. If you have questions, still ask me. I will answer them. But the most accurate definition of speed is... You know what? Maybe I should restart. Okay. No, I don't know why it's not going very well. All right. I know. Okay. So I'm going to continue on as it is, and whatever it is, if we have too much of a delay, we'll see how it goes. I apologize. I mean, yeah. All right. Well, anyway, so we're talking about the most accurate definition of speed, and I'm just going to go and I'm going to get a feel for how much of a delay we got. So if you want, you can put in your answer, and I'll see what kind of delay we got. All right. So the most accurate definition of speed is, while this is true, it's not the most accurate. While this is also true, oh, this looks much better. Good. All right, not necessarily accurate. While this is not going to be it because it's the time. Letter D is not it, and so that leaves us with C. It's the rate at which distance is covered. Now, how do you find distance? Well, we're all over the board, but so. By the way, Miriam Perez, I don't know if I know Miriam. I think I need to know. Well, whatever. Okay, you guys are great. Wow. All right, much better. Yeah, so right, that's why we're talking about it. So how fast you're moving is a pretty good definition. All right, but the displacement divided by time is sort of how you find the speed, kind of, sort of. But the best definition, if I were to pick one, now I'm not saying this is going to be a test question just like this because this is very, very particular. But yeah, the rate is very important. Whenever you have anything divided by time, so displacement divided by time, anything divided by time is called a rate. So the speed is the rate at which distance is covered. Okay, going with that, acceleration is the change in velocity over time. So that's also a rate. Again, this is very particular, and you'll probably, if you see a question like this on the test, you'll be able to get it, even if you didn't quite see this. But yeah, that's the best definition of speed. All right. Okay, one of the best questions ever, catch-up question. These names I just made up out of nowhere. They just kind of came to me. I don't even know if they're real names, but. So my runs away from Temo at 5 meters per second. If Temo waits, made up, 3 seconds and then runs at 7 meters per second, when does he catch up with her? All right. So, well, okay. So for serious though, these types of questions can throw you off. If you see one of these, remember there's 70 some questions on this test. And you've got to think fast, okay? You cannot waste too much time or spend too much time on any one question because you're literally getting roughly 1 minute per question on average. Now, some are going to take less than a minute, some are going to take more. This one will take more if you do it, okay? Well, in this case, like I said, these are just made up names. I have no idea. Just, coincidental that it has to do with anybody. So the thing to keep in mind here is that Temo's distance is going to be the same as Mia's distance, okay? And that's going to be the one main thing. That means when you, if you remember, distance is velocity times time. That means that Temo's velocity times Temo's time is going to be equal to Mia's velocity times Mia's time, okay? I should use uppercase M's there, but whatever. Okay, now the question is, that doesn't really help us. I mean, we've got Mia running. This is going to be whoa, all right, let's do that. Mia's velocity, the 3 seconds we're going to have to come back to, and then the 7 meters per second is the velocity of Temo. It's his velocity, okay? So we got 2 of the 4 variables. We want to find one. We want to find when he catches up to her, so that's going to be a time. But the question is, he waits 3 seconds. That's the other thing. So how do we get that? Well, we got to keep in mind that Mia has a 3-second head start. So she has run for 3 seconds more than Temo. So we would say that Mia's time is equal to Temo's time plus 3 seconds. All right. And once we do that, now we just have a system of equations. Like I said, now we just have a system of equations, and we just have to plug it in, but we can solve it now. So we can say, let's just kind of do this. So Temo's time. Actually, you know what? Let's plug in what we know. Okay. Oh, you got B. I don't know what the answer is. I honestly forgot. So I'm going to figure this out with you. So Temo's time is 7 meters per second. You guys are getting B, so it's good. or his velocity is 7 meters per second. His time is, we don't know. That's actually what we're trying to find out. Okay. We know that Mia's time or velocity is 5 meters per second. And we know that her time is going to be whatever Temo's time is plus 3 seconds. Oh, we're getting a lot of B's. We might be right. All right. So then what you got to do here is you just distribute the 5. So this comes 7 meters per second times time is equal to 5 meters per second times Temo's time plus 15. Those seconds are going to cancel out. Meters. All right. And it looks like B is the answer, but I haven't decided that yet. So I have like terms. So I got this. I'm going to subtract 5 meters per second t time from both sides, 5 meters per second t from both sides. So that's going to leave me with 2 meters per second times Temo's time is equal to 15 meters. So now I want to get t by itself. So I'm going to divide this by 2 meters per second. And you guys are way ahead of me, so that's great. So I'm going to take 15 divided by 2, and you guys are absolutely correct. The answer is B. Okay, so it's that starting point, and then using the algebra. I know some of you guys get caught up, or not caught up, but stopped, I guess, by the distributing here when you had to multiply this. But even before that, I know like just setting them equal to each other. So this is going to be basically your first step. And then you have to also just keep this in mind. That's not the final answer, but you get it. And then that goes plugged into there. That's how you solve those questions. And you are going to see one on the test, okay? So it's all just about working with those variables. All right. If you have a question, put them in the thing, type them in, okay? And then I'll get to it if I see it. Seems like we have a pretty decent lack of delay now. All right. But next question. Mia escapes Temo, and I was like, this was early Saturday morning when I was making this up, so forgive me for my weird stories. All right, but she escapes Temo and tries to run away again. This is the graph showing her position as she vainly tries to evade Temo. Oh, good. At what stages does she have negative velocity? So I'm getting A and C, A, C, A and C. All right, you guys are good. And you would be you're half correct. All right. The actual negative velocity here is only an A. And you guys are saying other ones, you might be confusing it with velocity time graphs. So this is a position time graph, okay? So B is negative. It's in the negative, yes. So B and C are both in the negative position. And if this was a, if this was a velocity time graph, you guys would be correct. In a velocity time graph, these would be negative, okay? Negative if a VT graph. But it's not a VT graph, okay? Right. What you're looking here for is, in a position time graph, is the slope. So at the beginning of the year, you guys did the tumble buggy lab, and you had to graph the position of the tumble buggy versus its time. You found the slope, and that told you its speed. So slope in a position time graph tells you its speed. All right. If it's a negative slope, it's a negative speed. It's going backward. It's got a negative velocity. All right. So in a position time graph, slope is speed. Speed is slope. Those two words are interchangeable in a position versus time graph. All right. You guys are great. So yes, it is only A. Good. All right. Same situation, but at what stage is she running back toward where she started? So looking, it's a position time graph. So you might have done walk the line a long time ago. Where is she running backwards to where she started from? Okay. So hint, she started right here. All right. So she ran away. She stayed put, and then she ran back toward where she came. And Ariadne has the other one, right? Both A or C and E. Okay, it's two of them, right? Because she's heading back toward where she started. All right, this is a position time graph, and her position is getting farther away and then closer and closer. All right. position time graph. It's the position, not her velocity. We're going to get to those. All right. Looking for questions. If you pop one up, I'll go back to it. All right. So at what stage is she not moving at all? This one should be easy. So when it goes up, she's going backwards. Yes. Yes. Well, hang on, Angelina. That's a good question. Backwards. See, we got to be careful with backwards. I'm going to go. So backwards is relative. That's why a lot of times when I draw a position time graph, I won't even draw this line. Okay. So if you say that she's going, Angelina, I would actually say you guys are answering it. You guys are partly correct. Noel got him actually, and it looks like Aiden got it. The answer to this question is B and D because it's flatlined. Her position is not changing, and it's not changing. It's staying right there. All right. So this is why, by the way, backwards is a word, and you have to be careful how you define it. That's why we've been saying negative direction. I've been saying it, but I'm not really writing it very well. Okay. This one is a little bit more accurate. So be careful. I'll be careful in my test questions. And if you're not sure, you just call me over and ask. All right. Yeah. So in this case, she's not moving when it's flat. All right. All right. Moving on. Okay. When is she moving at a constant speed? Moving at a constant speed. So so her speed is constant. I can't tell if that's a new answer. Sammy. Who's Sammy? C and E. Partly right, partly right, partly right, partly right. Partly right. Oh, wait. Sam's almost. All right. You guys are, I've been saying partly right, but no, you're right. It's ACE. So A and C and E. All right. Constant. Why is it constant? Because the line is straight. All right. It's a straight line. Okay. And in a position time graph, it's a constant change in position, which means it's a constant speed. All right. Good. Ace. I'd scroll back up. A lot of you guys got them all right. Very good. Ace is a word. Yes. That's why I picked that one. Yeah. So anywhere. So it's also A because it's still a straight line. It's a straight line. All right. Is the graph. If the graph was a velocity time graph, would B and D? Yes, Noel. If this was a VT graph, then these would be the answers. Okay. If. Okay. Yeah, so if those were a VT graph, those would be constant velocity. All right. Couple more of these, or maybe this is the last one. Yeah, I think this is the last one. What stage is she moving the fastest? Oh, a constant is 0? Yeah, Sam, good question, but moving. Gotta be moving. That's why it's underlined. You're right, though. It's a constant 0 speed. Okay. But the question said moving. Sorry. Yes. So, Sam, you are technically correct, which is the best kind of correct. All right, moving the fastest. We have 2 A's, 3 A's. All right, I'll just end it there because, yeah, why is it the fastest? It is. This is correct. Why? Because it's the steepest. It's the steepest slope. So she's changing position fastest at that point. It looks like the answer is A. All right. Good. Yeah. So it's steepest. So remember, slope is speed. Okay. They're synonymous with each other. They are the same thing when you have a position time graph. Okay. In a position time graph, slope is speed. And since we have a steeper slope, it's a faster speed. Okay. So, we'll see if you were paying attention. In a distance time graph, how do you find the speed of an object? A distance time graph or a position time graph. Yes, good. Yes, that's exactly it. All right, you find the slope. All right. I will say something really quick. No. Okay. not in a graph, okay? So don't use the equation if you have a graph. Don't use the v equals d over t if you have a graph. All right, I just want to be clear on that because that will trip you up. It will work sometimes, but not all the time. All right, so don't use the equation if you have a graph, please. All right, car accelerates at 6.2 meters per second squared over the course of 100 meters. What equation would we use to figure out how fast it needs to be going at the start if it needs to get up to 44.3 meters per second by the end? A lot going on here. I'm not asking you to solve it, obviously, but which equation? So what we have here, and I'm just going to say this is all the equations on the first part of the equation sheet. All right, this is all the equations in that first box. I'm seeing B. Let's see. So 6.2 meters per second squared is going to be our acceleration. Okay, 100 meters is distance. We want to figure out how fast it needs to go at the start. So going at the start would be VI. And it needs to get up to this by the end. So that's VF. So it looks like, yeah. So we want to find, we got VF. We know acceleration. We don't know time, though. We don't know time. So it is not B. It is not B. I see an E. Let's see if it's E. So VF. We got VF. Good. Do we have VI? No, but we're trying to find that. 2 is 2, so that's easy. We have acceleration and we have distance. So we have a winner, chicken dinner. So yes, that's it. So it looked like this would be it, but right, there was no, we don't have time. We didn't have time, so we couldn't use that. All right. So I purposely use this big log, like a brick of words here, because just to remind you that sometimes you need to go through and just find all the variables, identify them all. And you're gonna have scratch paper. So on a big question like this, especially, I mean, I'll give you as much scratch paper as you need, and use the time. Write this stuff down. All right. So just identify the variables that you have, and then no other. I don't think any other equation would work. So I think I purposely made that one up to BE. So all right. All right. So still in kinematics and motion, as you can see, there is some like. It loops around. We talk about the same stuff over and over again. So really quick, what's the acceleration of gravity on the ball at the top of its path? I see a B. So right here or here or here. Oh, you guys are so smart. Very good. Please don't get tricked by this question. The acceleration of gravity is always 9.8. Oops, other way, this one. Always 9.8. That's terrible. Yes, B is for, that's how you knew. Aiden, you got it. You read my mind. That's how you knew it. So it's always 9.8. On Earth, I should say on Earth. So I'm going to put a little asterisk there. On Earth, it's always not, that's an asterisk. All right, you know what? Just forget that. So it's always 9.8 on Earth, all right? Always. The questions aren't going to be always so clearly worded, though, so be careful with that. I'm not saying it's going to try to trick you, but just be aware. All right. I think this is the last part of this Unit 1. We got 4 different objects represented here. If you guys did the concept builders, this should look familiar to you. I stole it from them, like legit just ripped it off, but I think it's still helpful, so that's why I did that. All right, so moving in and this gets into our positive, this is like forward or backward, doesn't matter. We're talking about positive direction. So which one is moving in the positive direction and slowing down? Is it A, B, C, or D? A, C, C, B, bottom left, that would be C, A. I still don't understand those curved graphs. Okay, that's cool. C and A. All right, so remember that now we're into velocity time graphs. In velocity time graphs, you could quickly tell 2 things. You can tell D, A, and C. Maybe, could be more than one. So we could tell 2 things. We could tell, is it moving in the positive or negative direction? So if it's on top, then it's moving in the positive direction. So that eliminates B, and that's it. So B is moving in the negative direction because it's in the negative area. It's in the negative, it's got a negative velocity. Right away you could tell that. All these other ones have positive velocity. They're in the positive quadrant is the word I was looking for 5 seconds ago. Okay, and then slowing down. Slowing down means that its speed is getting closer to 0. So which of these is getting closer to 0? Well, this first one, A, starts out kind of high. Yeah, I know. So, right, so get ready for that. So that means that this one is slowing down. I guess I could just circle the A. So this is slowing down and it's in the positive direction. But so is C. Now it's more fun to circle all of them. Okay, so that one is also slowing down. This one is moving in the positive direction, but it's starting at 0 and getting away from 0. So this one is actually speeding up. So it's not that one. Okay, so two things. Okay, first is direction. Is it going positive or negative? And the second thing is the change in velocity. Is it speeding up, slowing down, or staying the same? All right, so if it's in the direction, is it above the line in a velocity time graph? That means it's going in the positive direction. Below the line means it's going negative. The curve. Angelina, you're okay. Right to the point. All right. So the curve means it's starting. We didn't really get into curves with velocity time graph too much, but here's what it really means: is the velocity is not changing a whole lot, and it's getting slower and slower, and then by the end here, the velocity is changing really quickly, and it gets slower really fast at the end. That's all that's happening. For the straight line, it's decreasing its speed at a constant rate, so it's getting slower constantly, right? For this other one over here, what's going on here is it's speeding up, and it speeds up really fast at first, and then it sort of is still speeding up, but it's not speeding up as fast as before. The dog's trying to get in my room, but she can't. So that's what those curves mean. Don't worry about the curves. They're not on the test for velocity time graph curves. You're not going to see those, but that's what they mean. Okay, focus on these two things, and you're going to be good. That's supposed to be a circle. Not good at this game. Alrighty, now the motion. Okay, which of these is getting faster? Which of these is getting faster? And Angelina, if I didn't answer that question well enough, let me know. Getting faster, getting faster. All right, good. You're still with me. Great. B and D. All right, so getting faster, a bunch of D's and B's, means it's getting away from 0. It's getting away from 0. All right. This one is starting away from 0 and is getting closer to 0. So it's not A. You guys are, man. All right. Letter B, which some of you guys said, is also starting away from 0. Backwards, but it's away from 0 and it's getting closer to 0 velocity. So it's not that one either. Letter C is starting very far away from 0 and getting closer to 0. So that one's slowing down. Also, it's not getting faster. Letter D is starting at 0 and it's getting farther from it in general. So the answer is D. Okay, you see why? Do you see why? It doesn't ask about direction in this case, but it is definitely getting faster. All right, do you see what I mean though? So getting closer to 0 on a velocity time graph means that the velocity is getting closer to 0. Closer to 0. Closer to 0. Slowing down. This one's getting farther from 0 on a velocity time graph. Try to, maybe later on, write these down. Position time graph, and then velocity time graphs to keep them straight. If B isn't getting faster, what is it doing? B is not getting faster. It's slowing down. So it's doing two things. Don't forget, it's two things. What direction is it going? It's going backward. So it's going backwards because it's in the negative quadrant. It's like if somebody was in the car and they had the reverse on, and you graphed the last part where they were going fast and they decided to slow down to a stop. All right. So velocity is 0. That's what they're doing. So going backwards and slowing down. That's what B is doing. All right. I'll come back to it if I need to. You guys are doing good. All right, which one's getting faster? Back to basics. A and B, just A and B, B, A, B, A and B. All right, once again, which one's starting at 0 and getting farther away from it? This one is, so it's A. This one starts at 0 and gets away from it, so it's that one. This one starts away from 0 and gets closer to it, so it's not that one. A and B is the correct answer. Okay. The letter A is getting faster, going in the positive direction. I saw, good addition. All right, so this is going in the positive direction, getting faster. This one's going what we might call backwards or in the negative direction and getting faster. This one's going in the negative direction, backwards, whatever, and getting slower. Pause for effect. All right. Now, one last question. I think this is one last question. Which one's changing direction? Yeah. Which one's changing direction? So velocity time graph now. So remember, where in the velocity time graph does it tell you direction? Good. Don't get tricked by C. C looks like it's changing direction, but it's in the positive the whole time. C is always going positive. Oh no, Noel. Oh well, that's okay. It's going positive, but what's happening at C is it's slowing down. Right, okay. If you don't get, so right, whenever you have an angle or anything like that, break it into parts. What's it doing? Just follow its path. So it is going forward and slowing down. Then it starts to continue to go forward and speed up. All right, so it's two parts to this. This one is always in the positive as well, where it's going forward but slowing down. That's not it, by the way. That's not the answer. And then it gets to a certain speed and just stays at that speed. All right, it never really stops, but it just slows down to the slower speed. Always going forward. This one is going forward at first, positive. It slows down, and stops for a moment. And then what does it do? It starts to go backwards. It starts to go in the negative direction. All right. So don't necessarily, maybe if you're having trouble with these ones, try to see it not so much as a bend, but try to see it as two separate parts. And once you realize that this is like just one line getting slower in the positive direction, and then this part here is just another line going in the positive direction, getting faster, it does get a little easier. Break it up into its parts. So this is two parts as well. And believe it or not, this is two parts as well. So yeah, that's how you approach these ones. You just break it up into their parts. I keep saying don't, like how dare you? But I mean, try not to let the bends like that get to you. All right? Okay, summary. So make sure you know all the parts of an experiment: independent variable, dependent variable, constants, etc. Make sure you can solve for any variable in those kinematics equations. I kind of did the one, okay? Just make sure you do all those. And then the one we're just working on, speed, direction, and displacement from a distance time graph or velocity time graph, all right? So for a distance time graph, I'm just gonna go in order here. Speed is slope. Direction would be also positive or negative value of slope, okay? And the displacement would be just to basically read the graph. How much go over then up? How much did it change? For a velocity time graph, the speed is going to be read it. I'll answer that in a second. To find the direction, is it positive or negative quadrant? And then the displacement is area. What is that? Area under the line. Okay, area under the line. Area under the line. All right. Okay. Angelina's question first. So with the velocity time graph, what's up with the direction? Okay. Yes. Like, okay, so look at here. So direction for I think I was answering that as you answered that. So in a distance time graph it's the same thing. A position time graph is the same thing. If it's a positive slope, so if it's sloping upward, whether it's curved upward or whatever, those are all positive slopes. In that case, it's moving in the positive direction. If it's going downward, whether it's curving downward, whatever, it's curving, it's generally downward. So those are all negative directions, backwards, if you might call it that. All right. When it comes to velocity time graph, the direction is literally just, is it in the positive or negative quadrant? Is it on the top or on the bottom? All right. So the PT graph, it went negative. Yeah. So a PT graph, it doesn't matter if it goes negative or not. It's all about the slope. All right. So I hope that answer made sense. I think I understood your question. And how do we find displacement again? Well, like I said, if it's a position time graph, you just read it. You just go over then up. You could add them together if need be, but you'll see that in the review guide. But area under the line, so that's when we had to use. You got to find all the little triangles and all the little rectangles and add them together. Okay. It went backwards. The line went up to one of the DT graphs. No, I meant it went backwards if the line went up. Oh, you're talking about, okay, way back here. Where was she running back toward where she started? That's what I think what you're asking me. That's because this is defined as her starting point, okay? We could call it 0, but it's not 0. It's just a starting point. So here she ran away from that starting point. Here she ran back toward it. And then also here she ran back toward the starting point. So I think that might be what you're confusing it with. So in here, she ran away, which you could call a negative direction. She ran away. And then in C and E, she ran back toward the positive, back toward her. This is why you got to be careful with how you label things. Okay, yeah. But do you see what I'm saying? Yeah, it is a little confusing. So I get where you're getting. I get where your confusion was coming from. But that's the answer. All right. Okay. So, Unit 2. And, all right. So that was hard. And I don't think we're going to spend quite as much time on these other units as before, as that one. But we'll see how it goes. So, Newton's law of inertia. What is it? No tricks. Yeah, it's all of them. It's all of them. So it's all true. It's all true. All right. Yeah, pretty much. All right. So just remember that's the general idea. Okay. So which one has more inertia? A bowling ball at rest or a small marble rolling across the table, and why? So it is A. Yep. Why? More mass. Mass is inertia. All right. More mass means more inertia. Mass is it. Velocity has nothing to do with inertia. It's just mass. Just remember that. Mass is inertia. Good. All right. If an object, constant speed, constant velocity. Okay, I shouldn't blah through this. It's moving at a constant velocity. You can be sure that, so it's constant velocity. What can you be sure about? That there's no net forces and all the forces are balanced. That there's only, well, you could read it, just enough force to keep it moving and it's canceled out. And you can't be sure of any of these things. Curious. Caitlin, I don't know if you're answering for now or for last time. I should have paid attention. Come to think of it, Angelina and Noel, I'm not sure either. I'm going to assume you guys are answering for this one because you'd be correct. So nice job. Yay. All right. Yes. So how do I put this? This letter B is wrong because there's only enough force to keep it moving. See, that's not how it works. If all the forces are balanced and there's just enough force to keep it moving, meaning like you've got friction pulling backwards and you have just enough applied force over here to keep it moving, forces are balanced. There is zero net force. Okay, so F net is zero. There's no net force. So that's wrong. That's why. The way it was worded. Any net forces are canceled out. Once again, it's sort of just the way it's worded. It's kind of below, what do you call it? It's garbage. It's nonsense. That's what I was looking for. And you can, yeah, letter D. I just was trying to play along with you a little bit, but it's definitely A. All the forces are balanced because here, I'll summarize it for you. Constant means balanced. Okay. Forces are balanced. So balanced forces. Okay. So constant velocity means balanced forces. There's no acceleration. All right. No net force. All right. Or no net force. F net equals 0. So if an object moving at a constant velocity, wait a second. What the? Looks like I have a double. All right. Well, guess you know the answer to that one. We'll skip it. So when you throw a ball, why does it keep moving once it leaves your hand? You should know this. I worded it funny too, so you might not know the right answer right away. Good one. Good guess. Good guess. All right. Wonderful. You guys are almost all incorrect. That is the most common incorrect answer, okay? The ball has already left your hand, okay? The ball is now flying through the air. So, yeah, it's not correct. So, why, though? And it doesn't remember anything, so B is not correct. There is a net force acting on it. That's not why it keeps moving. Why does it keep moving? Is because it has mass. And why mass? Mass is what? Inertia. All right. All right. Once it that's not why it keeps moving. This is why it would slow down. Slows down. All right. So once you throw a ball, any air resistance, whatever, is going to slow it down. I mean, gravity might. Just keeping it simple. Why does it keep moving? Why does anything keep moving? Once it's moving, it keeps moving because it has inertia. And what is inertia? It's its mass. All right, mass is inertia. Inertia keeps it moving. An object in motion will stay in motion because of its inertia. All right? All right. Yep. I don't know some of you guys. This is fun. You guys might be complete internet strangers. I was told to stay away from you. Should have been like momentum or inertia. Yeah, well, it is. It is. All right, you guys' favorite ones. Now, I know some of you guys love these ones. Which represents the forces acting on a car moving at a constant speed? Constant speed. Keyword is constant. Oh, hello. I know Mr. Goveville. He's my next door neighbor at school. Welcome. Yes, I know, Noel. I know you love these. Just remember, constant, all right? Constant speed. What has to be going for constant speed? Awesome. Well, I hope this is helpful. I really do. All right, constant speed. Remember, constant means what? Constant speed means balanced forces. All right, no net forces. All right, it's not A because there has to be some forces acting on the car. All right, Mr. Zwartz representing too. Mr. Zwartz's students, Christian, nice. All right, all of these are not balanced. This is not balanced. This is balanced. Ooh, we have a winner. This is not balanced, and this is balanced. All right, so if you removed all the air resistance, H could be the answer. But it has to be balanced. Yes. It has to be balanced. They better pay me is what I'm telling you. All right. Yeah, it's J and H. So balanced forces means constant speed. right? That's the big takeaway from this one. Okay, you got it? Constant speed is a key, is a little buzzword. You see that? You see that word? There should be a little flashy light in your head that says something needs to be balanced. Oh, we're talking about forces. I bet it's that. So balance forces if it's constant. Got it? Good. All right. So then it's sliding to a stop while moving to the left. Okay. Think it through. It's sliding to a stop while moving to the left. There's only one of these. Don't be so confident, Mia. Sliding to the left. Got a D, an I, an L, a B. Wow, all right, awesome. Whoa, my sound is just spiking off the charts. I need to be quiet, apparently. All right, I'm shouting, getting all excited here. All right. So, remember, these are not velocity. They are forces, not motion. All right. We can't tell by looking at them what direction they're moving. So it's the forces acting on them. So moving to the left and slowing down means that something has to be pushing it to the right. We have to have a net force pushing it to the right in order to slow it down if it's moving to the left. So that means it's got to be D. Some of you got it. Okay. Now, some of you guys said B, and you were close. You were close with B, but it's sliding to a stop. That means nobody's pushing it. So B is okay except for this part right there. All right, there's nothing pushing it to the left. Howdy, Faith. So you're awake. Good. So nothing is pushing it to the left. And so that's why B can't be right. That's why B cannot be correct. Okay. This one is hard because the velocity is to the left, but the forces, net force is to the right. So it's slowing it down. Okay. Let me clean this up a little bit. So just to reiterate, this is the force of friction while its velocity is going to the left. So got it? Friction is slowing it down. It's sliding to a stop while moving to the left. These arrows represent forces, not velocity. Got a second chance, maybe. Which of these represents forces acting on an egg falling at a constant velocity? Nope. Getting awfully loud. I had to turn down the speaker. Hopefully it still works. Let me know if I'm too quiet now. Tap. Okay, egg falling at a constant velocity. Alrighty, looks like it's H. You are correct. Why? Constant means balanced. Very good. All right. And it's falling, so you know it has to be going up or down. So it has to be that one. There's nothing going side to side. It could be, wait, somebody said F. Yeah, nope. Could it be something else? No, it could be one other one. Did anybody say it? I'm not too loud or too quiet. Awesome. Now, it could be J, maybe. Kind of, sort of, but probably not. Actually, the word falling kind of tells me it's not this one. Falling means it's just falling all by itself. All right. Why not G? Because, good question. Because if it's just G, that would mean this is the force of gravity pulling it down, and there's nothing to balance that out. There's nothing here, which means it's going to be going faster and faster and faster, and so you won't have that constant speed. All right? That's why. It's not balanced. So constant means balanced. Always remember constant is balanced. Okay? Constant's balanced. Constant, balanced. Okay. So, which of these represents the forces acting on a sledder moving to the right while skidding to a stop? If this one sounds familiar, it's because it is. I just asked this question 1 ago, previously. So, moving to the right while skidding to a stop. Sam, hold your horses, man. We're only on unit 2. Holy cow. I gotta go faster. We gotta go faster. You guys are doing great. All right. Moving to the right while skating to a stop, which means that there has to be a force pushing it overall to the left to slow it down, which means it does have to be E, right? So this thing is moving to the velocity is to the right. So that means the force of friction is pushing it and slowing it down. All right. Got it? So the velocity is to the right. Remember, these are force arrows, not velocity. So, good. Why isn't I right? All right, let's see. Oh, good question. It was actually kind of funny because it's not right because of this part right here. It's not, it's a sledder, so there's nothing pushing him to the right. He's just sledding. He's just sliding. All right? I know, right? I don't know how this happens. This is why I couldn't, this is why I didn't do it in class. Because it goes so fast. You guys are giving me, like, this is good stuff. You guys are giving me a lot of interaction. It's giving me a lot of good questions to answer. So, but the reason it's I is because there's nothing pushing it to the right. It's just sliding to the right because of its inertia, because it slid down a hill or something, who knows what. All right. Yeah, we're gonna breeze through the next 2 units because, well, we just did those. So it shouldn't need too much. All right. So box is pushed with 5 newtons to the north. Holy cow. All right. East, 12, and then there's 2 newtons of friction to the south. 3 newtons of friction to the west. We got all 4 directions represented here. I'm going to draw arrows to represent them. All right, I'm just going to draw a little box. You guys maybe could do, I'll go slightly slow, and you guys can maybe like figure this out. So this is 5 in the north. So east, so never eat soggy waffles. So east is this way. 12, I guess I'll draw it bigger. 2 newtons to the south. Oh, it's a little person, little guy, little arrow. 2 newtons and 3 newtons this way. All right, I got this. Now what? Ooh, somebody's got it. Oh, Sam. All right, I'm going too slowly. All right, so what you got to do is remember a couple things. First of all, add if you can. So the order of operations I like to do is add, then subtract, which is kind of the same thing. So you're adding a negative. And then a squared plus b squared equals c squared. That's Pythagorean theorem. So order of operations from easiest to hardest. And then if you have to, which you probably won't have to for this test, then you have to do SOHCAHTOA. Okay, that's the general order. So adding, there's nothing I could add here, not in positive terms anyway. But I could subtract, which is negative adding. So I get the 5 and the 2. And so what ends up happening is I get a 3 going to the north because the 5 and the 2 sort of cancel each other out a little bit. And we got a 3 and a 12, and I did this poorly. So I'm going to, that's supposed to go into the east. Wait, how do you find net force again? That's what I'm doing. That's what I'm doing. So I'm adding, now I'm subtracting. So 12 minus 3 gives me 9 to the east. All right. I cannot add those, and I cannot subtract them because they're perpendicular to each other. So this is the one where I have to do the Pythagorean theorem, because basically what happens here is they make a triangle. And you know that this is a 9 and this is a 3, and so you have to find the hypotenuse. All right? So 3 squared plus 9 squared is equal to, we'll call it net force, so force squared. So where's my handy dandy calculator? A lot of you guys are saying, oh, wait, you got an A, I'm not sure. So 3 squared plus 9 squared gives me 90, and I take the square root of that, and I get 9.5, which is A. All right. All right. So this goes up to 90 is equal to F squared, and then I want to take the square root of that. I don't want F squared, I want F, so that equals what did I say, 9.5. Okay. Yeah, I know. That's why I want to do this one, because it gives you all of those. That's and you know what? A lot of people forget to take the square root. That's a very dangerous step to forget. Fortunately, I didn't have 90 as a choice here, but that's been known to happen. All right. That's why we're reviewing. Oh wait. Angles and SOHCAHTOA. All right, this one is not as hard as it looks. Okay, you may have horrible, shadowy memories of this kind of thing. I know, but it's pretty straightforward. We want to find the weight, and I'm going to show you. I'm not gonna like watch. The weight is the force of gravity. We want to figure out how much the force of gravity is pulling it downward. Okay, so these are all in balance, which means that if gravity is pulling that downward, that means that the tension force, look at that, the tension force needs to be balancing it out. All right. So what that means is that this and this working together are balancing out the force of gravity pulling downward on that block. So if we can find these, we're good. All right. And I'm just going to do that. So the angle is 27 degrees. The tension is 70 newtons. All right. And going back to an old habit, hopefully you're going a little faster than I am. I'm going to label this. This is the hypotenuse. This side over here would be the adjacent side. And these sides over here would be the opposite side. I like to do that because then I don't get it mixed up. Okay? Because now when I think of SOHCAHTOA, SOHCAHTOA, well, I have the hypotenuse, 70. So I could actually, if I want to write it, I'm going to write it out. So hypotenuse is 70 newtons. My angle, well, I'll get to the angle, I'll get to theta. The opposite side is what I'm trying to find. Okay, this is the opposite side, not 0. And I know my angle. My theta is 27 degrees. So since I have H and I have opposite, I'm going to choose, here's H and opposite, I'm going to choose SOHCAHTOA. See, down here, this would be hypotenuse, but adjacent. I don't need adjacent. I don't care about adjacent. This has adjacent and opposite, but no hypotenuse. So I don't need any of those. So I'm going to use those. So, yeah, we're going to have the equation sheet. All right. So basically what you got to do boils it down to this. We've done this a few times. H times the sine of theta will give you the opposite side. All right. So then all you got to do is H is 70 newtons times the sine of 27 is equal to, I don't know. So H is what I got, 70 times the sine of 27, 31.8 newtons. All right. And that's one side. So that's going to be right here, this side right over here. But there's two of them. So they're both pulling with that amount of tension. So I'm going to have to multiply that by 2. Yes. And so I get what? 3.6 newtons is going to be my total final answer. So it looks like the closest one is 63.6. That would be this one. All right. See how I did that? So, bottom line is, if you have the hypotenuse, and good, nice, and you want to find the opposite side, then you're going to use this equation right here, okay? The H times the sine of the hypotenuse. You see how I solved that pretty quick, and I was trying to explain it. So you could do that. If you remember that, if you do that, do the equation, or the practice, if you remember this, I wish we could do, well, we can't. If you remember it though, this is a very quick question, and yeah, expect to see one on the test. Okay, but once again, this is one question out of 70 whatever, and so if this is one that you don't remember how to do it, come back to it. All right, save it till last. Guess if you have to. All right, sometimes you can eliminate them. I don't know, maybe. All right, so that's how you do it. How many questions are gonna be like the test? Probably just one, all right? Because asking more than one of these is going to be like unfair. It could be quick if you know what you're doing. I did something. There we go. It could be quick if you know what you're doing, but even still, it is a process. So it took me a few minutes to do, and there's not going to be very many of those on the test. At the beginning, he said 77. There you go. I don't remember exactly. That sounds about right. Roughly that. All right, an unbalanced force causes an object to, or is canceled out, or always causes acceleration, or causes a change in motion, because if it's large enough. I'm gonna wait. I don't even know how long the delay is anymore. I used to say 15 seconds. That was completely not true now. At the beginning, you said 77. So A, good, quiet, good. D, all right. C, wow, we got almost all of it. So nobody's chosen B yet, and I'm going to say that is incorrect. It's not. The whole point of unbalance is it's not canceled out. So, no, it is always going to. I'm glad. Yeah, it's always going to cause a change. It's always going to cause an acceleration. All right. It's not going to be this because it might cause it to stop. Could stop something. All right. So it's not that because of that. If it's large enough, not necessarily. It's always it'll just cause a small acceleration if it's too small. So so it's C. It's always going to cause. So just remember that unbalanced force always causes a change in velocity, and it might be positive or it might be negative if it stops it. Nice. Whatever that means. Okay. Black dog is pulling on the rope. What is the reaction force? Beep. Beep. Take the verbs and switch them. That's it. No matter how ridiculous it sounds sometimes. Good. Take the verbs and switch them. That's all you got to do. It's just that easy, no matter how ridiculous it sounds. Okay? Remember that. Take the verb. Holy cow. It's getting late. Take the nouns and switch them. Take the nouns and switch them. These are nouns. Okay? And switch them. I think this is the last one for this unit. All right, small car going 20 meters per second hits a large truck that's at rest. Which one experiences the larger force? Larger force. Yes. All right. Let's see. They're equal forces. It's always opposite and equal. Opposite and equal. Okay? Good. Good. Opposite and equal. Opposite and equal. You're going to get thrown off. Small car, large truck, opposite and equal every time. So for unit 2, solve any variable in the forces box except that last one. That one has like a mu in it. You know, that one. Don't worry about that. Identify any forces and the arrow that represents them. So we did that with the boxes. Make sure you know what tension and friction and applied and normal and all those things are. Make sure you know the difference between mass and weight. Okay, even if you just remember this, then that's going to help you tremendously with mass and weight. All right, weight is just the force of gravity pulling down on you. Mass does not change. Weight changes depending on gravity. So if you go to the moon, your weight's going to be different because the force of gravity is weaker there. All right. And once again, you saw it happen just the last question. Know that when two objects apply forces to each other, the force is always the same, even though the effect of that force might be different. Angled boxes. Aiden, you saw what there's going to be. All right. You saw whatever you saw what I told you. You saw what I just went over. So let that be my answer. Incline, however you put it. You mean like, so here's an incline and you have to solve the forces on the box and what is this and that. I did not go over that tonight. Okay. Any other questions? We're halfway done with the units, but there's not very many slides left because Unit 3 is the most underrepresented unit on the test. There's only a few questions for Unit 3 in 2D motion, which you'll be happy about. But make sure you know this one. Which one hits the ground first? A ball thrown horizontally, really hard out the window, 60 meters up, or a ball just dropped from the same window. This is important that you know this one, okay? Because the whole idea, good, yeah. The whole idea is that gravity affects things the same way, all right? So when you get a ball thrown sideways, it has horizontal. I'm glad everybody's saying C. Perfect. Good, good, good. It has horizontal velocity, but that does not affect the vertical velocity. Okay. The Vy, they don't talk to each other. They don't even like each other. They're in the same class, but they pretend each other doesn't exist. Okay. Unless you can throw fast enough to make orbit. Yes, Sam, please. Not now. This is not the time nor the place for orbital mechanics. Okay. Yes, good to doubt that. All right. So they hit at the same time. The ball thrown upward has initial acceleration of g and initial vertical velocity of 21 meters per second. What's the acceleration on the top of the path if it climbs to 10 meters? Better get this one right. There's a long delay. There's a lot of thinking. All right, remember a while ago I said, you guys got this one right a while ago. When I asked it very simply, Aiden's got it. Oh, I'm sorry, Angelina's got it, and Alyssa. That's it. Don't let all the words trick you, all right? It's muddling, it's messing with you. It's always gravity. It's always gravity, all right? That's all there is to it. Whenever something is thrown up in the air, I lost my pen. All right, it's always gravity. All right. G, always the acceleration. Watch out. Not velocity, acceleration. You're sitting near the center of a merry-go-round and your friend is sitting near the edge. Who has greater rotational speed? Ooh, oh, man. Sitting here too long, I guess. All right. Who has greater rotational speed? Wonderful. All right. I believe I have there we go. Saw this one in the other review too. So you are sitting near the center. So this is you. And here's your friend over here. Why is it let me just make this official. Okay. Oh, hang on. Whoa, 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 whoa. Sam, you're correct. Sam's correct. All right. Good. First of all, I'll answer that one in a second, Angelina. Everybody's wrong because we're getting confused rotational speed and tangential speed. Or there's another word for it, tangential speed, or linear speed. Okay. Rotational speed is if you just think of a disc spinning, how fast is it spinning? RPMs, rotations per minute or per second or whatever you want to call it. So everybody on this merry-go-round is spinning at the same rotations per minute. All right, you're all going around. If you were to time each other going around, you would have the same time because you're at the same rotational speed. So you see, even I got caught up in that. And so you had to watch out for that. I know, I'm sorry, Aiden. I'll give you extra credit tomorrow. Not really. Well, maybe I will. I don't know. We'll see. So that's rotational speed. So you're moving at the same rotational speed. Now, who has the greater linear speed? And then I'm going to answer your question, Angelina, in a second. Don't worry. This is for later. Good. Now it's your friend who has the greater linear speed. For the reason you guys were all thinking, your friend has to go a much greater distance in the same amount of time. You only have to go around a little circle. Okay? So they're going much... It's actually B. So your friend has to go much farther, and so they have a greater speed. It's actually kind of brings me to this point up here. Your change in distance, your displacement, whatever, your friend has a bigger circumference to go over the same period of time, so they're going to have a greater speed. So to answer your question, Angelina, that's what velocity is. It's your change in displacement or distance over time. Acceleration is just the change in velocity over time. So how much do you speed up or slow down or change direction? All right. And that goes back to unit 1. There's a couple questions about that here too. So if I put a little c by those have the same basic definition, but the equations are going to be different. All right, everybody get that one? All right. So summary of unit 3, told you to be quick. Use the linear motion equations to solve for variables. There's no angles. So and use the 2D linear or 2D dynamics equations. So make sure you can use these. And Angelina, this might be getting to your point. This is how you find the rotational velocity. I'm getting tired. The centripetal velocity is just by this equation, and the acceleration is by this equation, where you take the velocity, you square it, and you divide by radius. All right. Any last questions? I'm going to go through unit 4 pretty quick. All right. But type it if you got them. Type them if you got them. Not seeing any. I'm just going to take a drink of water here. I don't know, I think this only applies to mine, but maybe you could convince your teacher. If you don't have me. Hope you're paying attention. So little confidence, except for, okay, good, Caitlin. I like that. Sam, nice. All right. Nice, nice, nice. Very good. Hopefully an A. Lexi says A. Lexi, you better come on and say it, though. Say, I'm going to get an A by Lexi. All right? Mia's doesn't count for you. All righty. Good. Now, we talked about this one very recently. Well, all right. So you guys are actually answering the question, I think. All right. We saw this question in the beginning, except I asked which one has the most inertia. Now I'm asking which one has the most momentum. And the answer is good. Oh, no. All right. The answer is the marble. You guys are right, but why? And to answer it, what you already know is it's mass times velocity. And awesome. You're set, Lexi. It's mass times velocity. And so if the velocity is 0, then the whole thing's going to be 0. All right? Got it? Ask questions if you need it. All right. Lexi, calm down. You don't need to yell. How much force does a 5 kilogram object need to stop it in 20 seconds? I didn't read the question. That's okay. How much force does a 5 kilogram object, 10 meters per second, to stop in 20 seconds? And I put these over here for a reason. All right. When you have a situation like this, you got force. So I'm seeing B. You've got kilograms, which is mass. You've got 10 meters per second, velocity. And you've got 20 seconds, which is time. You've got F, M, V, and T. So you go to here. This one's not going to work for you. This one's not going to work for you because I. This I you don't need. Delta P you don't need. Oh, there's F. There's T. There's M. There's delta V because to stop it. So it's slowing down. All right. So we're going to use these two things here. And yeah, I think, let's find out because I don't remember. So force times the time, 20 seconds, is equal to the mass, 5 kilograms, times the delta V. So you could say it's negative 10 meters per second. Negative, positive, I don't care. It's changing that much. Okay, so multiply. And so we're going to get F times 20 seconds is equal to, I'll just stick with the negative, 50 kilogram meter per second. Okay, this is seconds. So then I gotta get f by itself, so I'm gonna divide both sides by 20, divided by 20. And so f is equal to, what's 5 divided by 2? Is that 2.5? So it looks like it's A. Yeah, 2.5 newtons. You guys said A, some of you. The 50 you got, but you forgot to divide by 20 seconds. Okay, now, the key. Is the delta just negative or positive? Like, is that how you write it out in the actual? Okay. Angelina, you bring up a great question. So think of it this way. When you look into it slightly closer, it needs to stop it, right? So if you're stopping it, that means it's going to be negative. So technically, this is going to be a negative force, but there's no negatives here, so we're just going to go with the absolute value. Why does it change to n? Great question. So let's erase that. Oh, crud. What did I just do? Tink. There we go. Erase that. Or so it goes in. Right. Okay, you get it. Yeah, okay. So when I take it, basically it's kilogram meters per second, and we just call that newtons. How did I use P? Still get it right, but I'm not complaining. I don't know. I don't know how you got it, Christian, because that's momentum. P is momentum, and I wasn't asking for momentum. Interesting. I don't know. You must be a wizard, but I don't know. But yeah, I would do what I did and just pick out the variables that you need, and that should do it. So then, how much impulse? And Christian, you might get this one right. How much impulse does it take for a 5 kilogram object moving at 10 meters per second? How much does it need to stop it in 20 seconds? So impulse, we need. I'm gonna go slow. Mass, velocity. Do this one. Hey, this looks familiar. Time. Impulse. Not gonna be doing that one. Here's impulse. Oh, here's force. Here's time. All right, sweet. All we gotta do is multiply. So force times time. So literally just force. I don't have force. Dang it, I don't have force. All right, jump the gun there. So it's not gonna be that one. Impulse. Nope. Don't have force. We got mass. We got change of velocity. All right, we do have those. So I'm good to go. So impulse is mass times change in velocity. So it's the 5 kilogram times the negative 10 or 10 meters per second. All right. And so you guys are saying B. Yeah, it is B actually, Angelina. You got it. You got it. Mass times change in velocity. So it's changing that much. That's how much impulse it requires to slow that down. Right. But once again, you just see how I did that. I identified what I have, what I need, and and so I just basically did this. I chose what equations I need to use by what do I have? Well, I have these. What do I need? I need impulse. So that's it. Okay, it's gonna be helpful to use your scratch paper when you take this test tomorrow or whenever. Couple more. All right. Now, how much momentum does it take? It's the same question. Look at this. I'm going to go switch back and forth. Same information, 5 kilograms, 10 meters per second, 20 seconds. Okay. So how much momentum does it take? And I'm just going to stop for a second. I have something to play with. No. E is correct. Why? Because impulse is equal to change in momentum. Literally, I know the impulse from the previous question, and I know it's the change in momentum, so it's got to be 50 because that's what I got last time for the impulse. All right, impulses change in momentum. Impulses change in momentum. Good. You guys are great. You guys are great. Okay, you guys are great for sticking with this whole time. All right, what we got? A couple more? Yeah, a couple more. So, a couple more. Why do you feel less force when the driver of a car stops gradually compared to when they stop suddenly? Could we, let's go back to that. Yeah, kind of Faith, that would work in this case. But what if it slowed down to 5 instead of to 10? In that case, you would basically, that wouldn't necessarily work. All right, because then this would be 5. So you might get away with it, Faith. I'll leave it at that. So why? Why do you feel less force? And I worded it trickily. Seeing A, I saw B, A, okay, all right, all right. The answer is C. The answer is C. I'm sorry. The deal is you're not going to feel the same amount of force. This was the whole egg project thing. You tried to reduce the force. You were trying to get the force lower. All right. It's not the same force. It is much less force. Okay. So it's not A because you're trying to reduce the force. It is C, I know. It's not less impulse because the whole idea is impulse is force times time. And if you increase the time, you're going to decrease the force. So the impulse stays the same, but you're manipulating, like with the egg project, you tried to increase by adding the padding, it slowed it down over more time. And so you increase the time it takes to stop. All right. So since you increase the time, there's not less impulse. So sorry, it's the same impulse. So it's not B. And the same thing for D. But that's just kind of, yeah, I know, right? Here's the deal. Less force, more time. Chances are, if you see those two words, if you see the word force and time together, and they're talking about feeling less force, like the egg project, like if this question rings true, if this is like reminding you of the egg project, okay, then here's your egg falling. All right, if this reminds you of the egg project, then this is probably the answer. If it involves force and time. Less force means more time. More time means less force. Okay? It's a stinky egg, I guess. All right. Last one. All right. So we got a 0.8 kilogram motion cart moving at 2 meters per second. It hits another cart and it slows down to 0.2. The second cart was at rest and is now moving at 0.3. What's the mass of the second cart? You remember me asking this last time. Maybe you do, maybe you don't, but I asked this last time and it was on the test last time. And guess what? You're going to get a question like this tomorrow or on the test as well. All right. It's a lot of words, a lot of stuff. If you break it down, what's going on? Well, you got P equals mv, right? And momentum is not lost. So you have an 8 kilogram motion cart, okay, 0.8 kilogram. And it's moving at 2 meters per second. So 0.8 times 2 meters per second means that this thing has 1.6, the momentum is 1.6 in the units, kilogram meters per second. All right. The second cart is at rest. So how much momentum does it have? It's got 0. So P equals 0. All right. Now, well, here, wait. Forgot about the first cart. It slows down to 0.2. So what was its change in momentum? How much momentum did this first cart lose? Well, I want to find the change in momentum. And if I take the mass times the change in velocity, I can figure that out. So the momentum, or the change in momentum of the first car, is equal to its mass, 0.8 kilograms, times its change in momentum. And so it went from 2 down to 0.2. So it has a change in momentum of, if I do the subtraction here, that's going to be 1.8 meters per second. All right, 2 down to 0.2. So the change in momentum, I can't do that in my head. So negative 1.8 times 0.8, I get 14.4 negative. All right, kilogram meter per second. So that's how much that first cart lost, which means that the change in momentum of the second cart is a positive 14.4 kilogram meter per second. All right, so I'm just kind of working this out. I'm just kind of scratch papering it. I'm not following any kind of, does it have to be negative? again, this isn't the final answer. I'm just trying to like work it through, and putting a negative there makes sense to me because it's losing that no momentum. It just reminds me that the first card lost momentum, and then the momentum is going to get transferred over to the second card. Okay, so since the second card now has that much momentum and it started at rest, well, momentum is 14.4 meter square kilograms, whatever. Is equal to its mass times its change in velocity. And now it's moving at 3 meters per second. So if I want to find the mass, I just had to I had to divide both sides by 3. So I divide that by 3 and I get 4.8. Okay, mass is 4.8 kilograms, which isn't a choice here. All right, maybe maybe I did it wrong. It's got to be yeah. Thinking it's A, but let me see if I did something wrong here because I got 4.8, so I'm off by a decimal somewhere along the line. I lost that decimal, so 2 minus 0.2, 1.8 times 0.8 kilograms, 1.44. Oh, that's what happened. All right, this is actually 1.44, not 14.4. So that's where I lost the decimal point. All right. So that's what happened. So the decimal place moves over, and I get the answer of A. All right, when I do the actual math. What does P represent again? Momentum. P is momentum. Great. Did you get? Hopefully, you got that same answer then, Alyssa. Good. You guys are awesome. So the answer is A. All right. That's a hard one, obviously, but that's why I wanted to work it out. Just to summarize this one, the first card lost some momentum and the second card gained that momentum, and we used that to figure out the mass because we knew the cart's new speed. That's it. All right, you got it. Nice job. It is a final. So this is it. The other thing is that I didn't cover here is know the difference between elastic and inelastic. Otherwise, that's it. Okay. So I'm gonna wait. Let me know if you got any other questions. I don't know if, I mean, you guys stuck around for an hour and a half. That's amazing. So I guess, like I said, there's 70 some questions. I know, it's crazy. 70 something questions, 77, 74, I don't remember. So pick your battles wisely. Use the scratch paper, use the equation sheet that you're going to get, and keep moving through them. All right, you could flag questions and come back to them. Elastic means they bounce. Okay, no. So elastic means bouncy, and inelastic means they stick together. All right. So adding vectors. Good thing, Miguel, that there's not a whole lot of that on here. All right. Thanks, Mia. Yeah, vectors. Yeah, in the study guide, due date, take test. Yeah, exactly, Aiden. So what we just did was elastic because they bounced. Yes, Faith, you are correct. Adding vectors. All right, yeah. So thank you guys for joining me, and hopefully again this was helpful. I don't know if yeah, hopefully it's helpful. So you guys have a wonderful evening, and I'm gonna wait like a couple seconds. I pass person kind of. I'm glad I can be helpful to people who aren't my students because that's really awesome. Like I said, this is a big deal. I think spending an hour and a half getting ready for finals, but you know, this is how it is. We don't have it possible. I don't know. All right, you guys, awesome. So you have a good evening, and I will see most of you tomorrow. And you guys who I haven't met yet, well, say hi at some point, all right? So take it easy. Stream Minecraft, no. Aiden, get as much done as you can, all right? That's all I have to say. All right, take it easy.